at least for the time that I spent slaving over a hot code. So this was a simple code, but a lot of work refining it. Okay, as he said, this is open source security orchestration. My name is Gregory Pickett with Hellfire Security. I am part of the cybersecurity operations group and have been for some time. Overview of today's talk. We'll start with how this all began, followed by orchestrating all the things. Next is Behold Skynet, or what we're kind of building here, and then making it better. And finally, wrapping up, final thoughts, where to get A&P links to learn more about security orchestration. Okay, let's start then with how this all began. Okay. It started with a question. All right. Multiple cloud servers, all using fail-to-ban to protect themselves. Can I share a jail between these systems? But in security operations, this leads to lots of other questions as well. How do we get to threats in time? All right. How do we make sure that the evidence gets captured in the event we have identified a threat? How do we make sure that the threat is stopped before it's too late? And then how do we do this all with a limited staff? Now, these questions are because of the way that security operations currently works. We monitor the enterprise, process alerts. If we have a big boy shop, we'll have a SIEM and be looking at correlations. And in the event that we identify a genuine threat, we kick off incident response. And despite a multitude of solutions, this is still very much a manual process. Each solution is kicked off in sequence by us. As it currently stands, if I have a system, someone fails to log on multiple times, an address is jailed. If I want to jail that also on another system, running fail-to-ban, it's a very manual process. If IPS kicks off an alert, we have to go to the council, we have to take a look at it. In the event we identify a genuine threat, we then have to go to the switch, we have to start a capture. We find something interesting, they were successful, then we want to log into the antivirus, the endpoint protection product council, and we have to maybe instruct it to delete files, kill a process. So all of this is very manual work. A lot of time then is being wasted being a bridge between these systems. Okay. So as an operations person, I think as a human being, what I want is ultimately all these solutions to keep doing what they're currently doing and to directly talk to each other, to get what they need from each other, all right, and leave me out of it. I would like these things just to talk to one another. IPS talk to the switch talk to the endpoint protection, and they get things done. That's what I would like, and what inspired this. Okay. So how would this work? Right, sharing events. So an attacker fails multiple logons. Server A jails the attacker address. Server A shares those events with server B, and then server B jails the attacker address. Okay. Very simple use case. But there are other use cases. So let's take a look at other use cases for sharing events. We want to do more than just, ultimately, we want to do more than just share or fail to ban jail. Okay. Generate threat intelligence feed. Events shared between peers could be used to generate a blacklist, and then you can use that with anything that can consume a blacklist. Firewalls, endpoint solutions, detection tools. You could share the blacklist with vendors, partners, colleagues. Lots of uses for that. Firewall rule propagation. Host firewalls, network firewalls can receive events from peers and, of course, block the threat, the source of the threat events. And then distribute events among peers so that other host firewalls, network firewalls can then block the threats that firewall is seeing. Drop propagation. Drop source of threat events. Web application firewalls, intrusion prevention systems can distribute events among peers so that events that they have seen, threats that they've dropped, other web application firewalls, other IPSs can then also drop that threat. Prevent known threats. Host firewalls, network firewalls, receiving events, right, shared amongst peers, actually shared with an external third party, can block sources of threat events. Lots of publicly available threat feeds. NAT to honeypot. Host firewalls, network firewalls can receive events from peers and then redirect the source of the threat away from your assets. Right? NAT it to a honeypot. Host firewalls, network firewalls can receive events from peers and optionally slow down the source of a threat by natting that threat to target or any number of variations that seem to have sprung up over the years. Capture threat activity. Switches, routers, firewalls can receive events from peers and then run a packet capture on the source of the threat activity. Inject beacon. FTP servers, file servers, honeypots can receive events from peers and then drop a beacon in the path of this source of threat activity. Right? It'd be very nice if they would open that file, then run it, and then we'd know where they are at. Redirect traffic. Routers, firewalls can receive events from peers, change the route for the source of the threat activity, bring it through an alternate segment, one with additional sensors. You get a closer look, and of course the traffic would then just continue on to its normal destination. Reporting threats. An email server could receive events from peers and then report the source of the threat to the abuse address. Okay. Host isolation. Switches, routers, firewalls can receive events from peers and then apply an ACL, a bit different, to the target of threat activity. Additional logging. Switch, router, firewall, server, maybe an application, can receive events from peers and turn on verbose logging for the source of the threat activity, or could alternately also, or together, verbose logging for the target of threat activity to get a closer look at what actually happened after the threat activity occurred. And final one, trigger password resets. LDAP, Active Directory, Radius, TACACS can receive events from peers and then start a password reset process for the target of threat activity, let's say for web server, right? Web server accounts. Yeah. So what we're talking about, right, in a very simple sense, is security orchestration, or what I like to think of as machine-to-machine orchestration. And this is how we're going to do it. Adaptive Network Protocol developed this to share events between systems in a very common format, very simple format. Events are stored locally, and then peers can make use of the shared events how they see fit. Fail to ban can block the threat. Mod security can block the threat. IP tables can do natting. It can nat it to a honeypot. It can nat it to TARP. It can do any number of things. Okay. So how this would work in the original scenario. Fail to ban events are pushed into AMP. AMP sends those events to peers. AMP, of course, accumulates those events, and at some point in time ages them out, right? Ages out expired events because a threat today is not necessarily a threat tomorrow. Server B would, AMP would receive the events from peers. AMP would, of course, locally accumulate those events, and then those events would be pulled into fail to ban by AMP so that fail to ban could then jail that address, right, block that threat, and there will also be aging there as well. Protocol. Sharing for local peers is multicast, pretty simple. Unicast to remote peers. There are two types of messages right now, add threat event and remove threat event. So it's currently implemented. The operation sending and receiving with local peers on UDP port 15,000. I don't think that was taken on that long list of ports. That's the multicast. Received from remote peers on TCP port 15,000. And this is about security, so the message is signed with a SHA-256 signature. Some rules. The signature must be a known good signature. I do believe we actually check that first. If it's already known, do not share about it. Do not share it. If I know about it, so does everybody else. Let's not duplicate our efforts. And do not reflect back to the source. We don't want anything akin to a broadcast storm. Okay. The packet there, version is 1 byte. It is a binary protocol. Type is 1 byte. The event that's being shared is a variable size. Signature is 64 bytes. It's very signature heavy right now. Mostly signature. On the wire there, in Wireshark, we have pointers. We have the version of AMP, message type, the event, very short events, and then the signature. Okay. The messages we have here, we have the add thread event being carried by it, the remove thread event. They're 5 bytes each. Address is 4 bytes, time to live 1 byte. Okay. Let's look at some peering that you can do. Local on the same segment, like on the perimeter. Remote on the same network across the same location. Right, you want to get past the broadcast domain across the layer 3 boundary there if your router does not propagate multicast. Across different locations, an HQ to branch office, link up cloud resources. Most routers aren't set up to propagate multicast, so you would be remote peering within the cloud or between clouds. And of course, different networks. If you want to share events with a vendor, or if you are a vendor, you want to share events with a customer. Any trusted partners, government institutions, probably a dirty word right now, but you can, of course, do that. You can also share with individuals. That can do communities, different networks. Yeah. Pretty simple examples here at HQ. We have local peers sharing events amongst themselves. We have multiple locations. We have an HQ sharing among local peers, a remote site sharing among local peers, and then a remote peering between the two to propagate between locations to form a larger federation. It's two-way. Trusted partner vendor. We have an HQ, local peers, a vendor, local peers, and then a one-way remote peering to propagate events, but only in one direction, from the vendor to you, the customer. All right, we have varying degrees of trust with different organizations. Cloud assets, we have remote peering within an Amazon cloud, and actually the demo is very much like this. Remote peers within the Amazon cloud, we have remote peers in the Azure cloud, all remotely peered there, and then of course a two-way remote peering between the clouds to propagate events, and once again a bit of a federation there. So there's lots of different possibilities, including communities, right? Members of a community, individuals, we have lots of security researchers here, we have lots of hobbyists, we have people in the present profession, and not necessarily can you do this at your office, but you want to go ahead and share events between individual systems, you can go ahead and do that. Okay. You don't have to do a full mesh. I don't think mesh is used very, very often. It's more of a hybrid where you have maybe two uplinks. So you have sharing with two out, sharing to another direction, right? Getting kind of a hybrid network there. So we talked about use cases for sharing events. We talked about the sharing that goes on. Now we need to talk about, of course, how individual systems make use of those events. And those are done with interfaces. Okay. Purpose of the interface is to publish events to ANP and to pull events from ANP. Now, an interface starts out as a template. We have a variety of components, the supporting components, because they basically speak ANP. And you already set up, you just have to fill in then the reader and the writer, which speak the solution, speak IP tables, speak ModSec, speak fail-to-ban. Okay. The operations are publishing to ANP via the loopback interface, inter-process communication, and pulling from ANP via published lists. We have our same situation as before, but now with a bit more detail for the interfaces. ANP receives events from peers, it's accumulating them. The interface will then pull events from ANP so that threats seen by others are blocked by fail-to-ban. And the interfaces then pushes events to ANP, so ModSec and fail-to-ban events then are passed onto ANP for sharing. Okay. Two types of interfaces native. We're talking about an integrated solution, which in most open source situations it is. You are able to install the software, typically on a Linux server. So ANP is then going to be installed in that same system. It's able to read and write locally. Examples, fail-to-ban, IP tables, ModSec, any number of other solutions like OSSEC. Then there are surrogate interfaces. This is where we talk about using this with closed source solutions, where we have ANP installed on a different system, and it reads and writes to that remote standalone solution. Right? So we have one system that's running it, participating, sharing events, and then it has to then read and write remotely to, let's say, an ASA, right, through the API, or a switch, or a router. Okay. Same scenario again with the surrogate interface. So in this case, the interface is pulling events from ANP, so the threats seen by others are then blocked by the ASA or possibly added to a honeypot, and then the interface is publishing events to ANP. So the ASA events are passed on to ANP for sharing. Okay. Existing interfaces, right? We already have interfaces for this. We're actually using this already. We have a fail-to-ban interface. It pulls events, reads threat events from ANP, adds threats to the jail. It will then publish events by writing jail addresses to ANP. Because of ANP aging, this means that threats stay jailed for 24 hours as opposed to typical, I think it's like 5 minutes originally. We use it about 1 hour. Now, at this point in time, given the 24 hours, it's important to note that mistakes can be reversed. We all fat finger addresses. We were testing our ModSec installation, and we're tuning it a bit, and we make a mistake, and we have an event showing up in the log. We don't necessarily want to have ourselves then, we don't want our system responding to us. So there is a tool that allows you to inject a remove threat event, which is actually how we started off with the remove threat event message. So we can take ourselves out of that response. That too does have to be signed to make sure that a threat isn't then, of course, removing themselves. We have a blacklist interface, pulls events, reads threat events from ANP, and then adds the threats to a blacklist. You can distribute that for internal use or external use, detecting, blocking, threat indicator for analysis. ModSec interface publishes events to ANP, writes the attacker address to ANP. Pair with IP tables, and you can add an attacker to a honeypot. Speaking of that, we have an IP tables interface. It does pull events from ANP by reading threat events from it, and then adding threats to from a local web server to a local honeypot. It's good to throw in a high interaction honeypot at your website to log the activity, and good opportunity also for BruCON. This is where things get a little more interesting. Sharing also provides increased visibility. It's important to note that we don't change the enterprise. We're not changing how it functions. We're not changing how fail-to-ban functions. We're not changing how ModSec functions or IP tables. We're letting them all pretty much do the job that they always have done, and with the same expectations. What we're doing is giving them greater visibility to do so, right, so that they then have the ability to be proactive. So we have our expanded visibility here where an attacker fails their logins. All right, server A jails the address, server B jails the address, server C jails the address, server D jails the address. Now we have given server D, C, and B an opportunity to be proactive. We increase their visibility, and now they can respond prior to the threat crossing their threshold, right, before it gets there. Give them the opportunity to be proactive. Yeah. Also with sharing, we see a certain amount of cooperative behavior and the ability for the enterprise to act on its own. If anyone has any experience with the traditional paradigm for security orchestration, there's something called playbooks, which very specifically lays out how this system is going to respond in a particular situation, and then what's going to be done next by what other system, and so forth. This happens without a playbook, right? This happens based on the normal, natural behavior of these solutions. They start coordinating, they start acting together to make things happen. Okay. First example of some cooperative behavior where we talk about an insider scanning a server, sharing those events. Then the server shares those with server B with a switch, and the switch starts logging that intruder traffic. Okay. Gets a bit more extensive than that. Okay. Let's see how our systems start acting together. Okay. Acting to defend the network. We saw this when we started to use ANP. Okay. So an attacker fails multiple logons on one of our servers. Server jails the address, shares that event with other servers. Every single server in our infrastructure will then deny access to the attacker. Web application firewall nets that attacker address over to a honeypot. Okay. And that address gets shared with the interface for the blacklist generation. Blacklist is generated, and that is consumed by our threat detection platform. So now all of our customers are immediately notified anytime the attacker visits their network. Okay. Should it happen a different way, if they go ahead and decide to browse the website, maybe attempt a SQL injection, it's picked up, that event is picked up by ModSec, it's shared amongst the other servers, these servers know about it, they then jail that address, it prevents the attacker from logging into any of those systems. The IP tables then also having that event shared with it will NAT the attacker address over to a honeypot. And if it's a duplicate ultimately of the website, it should be seamless, shouldn't notice. And they begin browsing, scanning, and whatnot of honeypot instead. Right? And that address also then gets dumped to a blacklist. Our customers are now notified anytime that attacker visits their network. Right? So we also see systems acting to investigate a threat. All right? Insider scans a server, server shares those events, and through a surrogate interface, we also share them with these two switches. The first switch logs traffic from the threat source, and the second switch captures traffic from the threat source to the subnet. Right? So these systems acting to investigate a threat. Acting to respond to an incident. A website's defaced, maybe you have an OSSEC interface there, sharing that event out with other systems, shares it with a switch, firewall, LDAP. The first switch there isolates the web server by throwing down an ACL for the target of that threat activity, that web server. Firewall does the same to limit horizontal movement. LDAP receives that event and starts a passive reset process for web server accounts. So demonstrations. I did say that the first scenario we've seen emerge through our use. So we'll take a look at that. We actually have a network, small little network here. We're going to watch it defend itself. We have system 1, ANP1. It's actually in the Amazon cloud, assuming the uplink is good here. It's got ANP running, a couple interfaces there. ANP2 then, it's in the Azure cloud, also running ANP. They're all sharing events here. Various interfaces. The first one has a fill the ban interface, the ModSec. Second one in the Azure cloud has a fill the ban interface, blacklist interface, and then we have the third one in the Azure cloud running ANP, also with the fill the ban interface, ModSec, and IP tables. Hopefully we can see that. Is everyone able to see that? Now, that third one has the website. I suppose it's open season on this website now. Tempting target. So we are going to attack that first one. We're going to do what we see every single day, right? SSH brute force. And we're going to see that system share those events all the other systems, and we're going to see how they start defending themselves. In this particular case, this one is going to start natting me to a honeypot, and we'll see it looks almost identical to this. There's a slight difference, so that you can, of course, see that it is something different. All right, I want to show you how, since they are already participating in already showing events. I want to show, there we go. So they have, it's getting big. The longer these things stay out here, the more brute forcing we see. Surprise, surprise. So we see that their failed to ban jails are pretty much synced up. All right, there's some timing issues, obviously, but the first one has 123 addresses that are currently banned. Second one is 122. 3 will have a similar number. Right? They originate at different points and cascade across, and so you won't have an exact match unless it's very quiet. You can see the second one. I'm in the wrong spot. Okay. Typically with blacklists, we like to just have the addresses. So that's what we have here, and we have that blacklist sitting there that can be consumed by any sort of threat detection platform.
Can you maybe select the text? Maybe it's becoming clearer then.
Sure. That's easier to see. I can roll this up. So there's that first part. I'll not lose that though. So they are almost identical. And then we have the blacklist that's being generated off this that can be consumed in any number of ways, at infinite almost. It's being generated from that. So let's go ahead and exit from this and this. This is number 2. We are going to pound on that first one a little bit. It has been acting up. Failed to ban has not been necessarily banning me. If it should fail again today, I have other ways of pissing that first machine off. Okay, it's got set to 5, so we should be through this pretty quickly and know where we stand. One more. Been kind of on and off of that. Oh, it worked. Nope, it does not want to block me. All right, so we're going to try to upset it, piss it off in another way. Let me get one of those addresses. Good old ModSec should be able to help me out here. Okay. We're going to go to that first one again. And non-compliant as far as is concerned. All right, a 403. I did speed up the communication. They're sharing a little bit faster than we normally have them sharing, so we should start to see the cascading effect pretty soon. While we are letting those 2 talk, or those 3 talks amongst themselves, we will continue and check back toward the end here. Okay. So as I said, we've seen the first situation emerge. We've seen a self-defending network emerge. With our use, there are 2 other situations that are waiting to emerge. It's waiting for us to make it a bit better. We're talking about additional message types for the add target event and remove target event, so we can start doing things like dropping ACLs, so we can start seeing basically the use cases from before, start passive resets. It also means more interfaces. Right, LDAP interface, I would like to see an OSSEC interface as well pretty quickly. Cisco ASA interface, to bring out more of these use cases to allow some of these other situations to emerge. Also, peer groups. Okay, you trust different groups of people, different organizations, to varying degrees. Right, I might trust you completely. We've known each other many years. We can go ahead and share the events, all events. Maybe just met this guy. He doesn't trust you so much. He doesn't want you to see his events. So we have a peer group where we share everything, and then only some things with you. Maybe only things that originate with our organization. So after the establishment of peer groups, there's some sort of filtering to say that we are sharing only, you're sharing, and just us are sharing. We'd also might see some filtering for remove threat events. Maybe, especially in a vendor relationship, or a partner, we want them to share threat events, but we don't necessarily want them to have that kind of control, that kind of impact on their network, the ability to remove threats. Right? We want maybe just us doing that. Okay? Another potential use of peer groups is between systems that are going to be involved in any process. Any systems that would normally be involved in investigation, peer them up. Any systems that would normally be involved in incident response, peer them up. Okay. Future direction, Internet of Things. Okay. Not looking to be a researcher, someone involved in Internet of Things, so much as the opportunity to take a system on a chip, old school Raspberry Pi, put a bunch of circuit interfaces on that, drop that on a remote branch office network at the perimeter, and immediately give that network the capability, right, to start responding. Not having to re-architect the environment, not having to re-engineer anything, but just allow them with the system on a chip on this SOC to begin participating and to start to do these sorts of things. Also, reporting events. This is machine to machine. They are talking amongst themselves. They are acting on their own. I, at some point at time, want to know exactly what they're up to. Auditors who might want to know what they're up to. So if we had some sort of running audit log, or we could take a look every once in a while, maybe troubleshoot a problem, run a report, that sort of thing. And export to sticks and taxi. Not a big fan of sticks and taxi, but it's important that we share, right? Not just among these systems, but also different types of tools, so we can make the most use of this information. Okay. So all my talks have these two, obligatory slides, making the difference. All right, first one, machine-to-machine communication solves many problems, though it doesn't have to be the apocalypse. With it, we can get to the threat on time, we can make sure evidence is captured, and we can make sure that the threat is stopped. And we can do that with limited staff because the systems are acting on their own. Okay. Final thoughts before we check on those three cloud servers. It's common to kill problems with money and people. Right? Vendors want to come in with a really big, expensive solution. Understanding your problem zone means better results, right? Often cheaper results. Enabling synergies like self-defending networks, self-investigating networks, and self-responding networks. Now, before I finish up, I want to check on these systems here. We'll check at the end. There, our third system. That would be really horrible if it didn't kick off. It has not kicked off yet. Well, that one's no longer letting me log on. Try the second one. Okay, so they're talking. Let's try that third one. It's not talking. That's a horrible thing. Okay. Well, let's check in just a second. We have some time. Maybe they'll finally talk to one another during the Q&A. Famous last words are, the demo worked every single time when we were practicing. Okay. So So where to get AMP? I'm sorry, but it is at SourceForge. I know that it's quite common now for everything to be at GitHub. And I think with more contributors, we would move it to GitHub. But there it is right now, the AMP agent with the SHA-1 hash, should be updated to 256, of course. The interface for blacklists, interface for fail to ban, IP tables, interface, ModSec interface, everything's up there. Lots of links. I mentioned traditional security orchestration involves a very different paradigm where we have lots of controller-centric orchestration. Lots of companies doing it. Make sure you have a lot of money when you go there to visit because they're very expensive. We also have lots of open source, very specific use case orchestration for fail to ban there. We have more information on taxi and sticks. Also said IP tables, very specific use case for it to redirect blocked IPs to a honeypot. Okay. That is it. Before we do the Q&A, I'm going to cross my fingers and see this. If this has talked yet. There we go. It has finally spoken. Isn't there something we're supposed to say about the demo gods? Apparently they are happy. So, if you see a bit of a difference, right there, right? That reset password. So we now have those three systems sharing the events, and they've all begun to respond to me, the threat. They've stopped me from logging in. They've probably by this time added me to a blacklist so that customers know about my visit, should I attempt to contact any of them. And web servers and their web application firewalls are now starting to nat me over to very convincing looking honeypots so that I can be logged and tracked and possibly given a phone home binary. Okay. All right, good. Okay. So that is it. Thank you for coming today. I understand we're doing a Q&A. Okay. Questions? Thank you. It was a lot of work.